All right, so here is exercises 3, 4, and 5. Uh, for exercise 3, remember you can, if you're stuck, you can always watch a little bit of these to get a hint at how to proceed, but the more you try to do on your own, the more you're going to get out of it. If you just watch me do the whole thing because you don't know what to do, and then just write down what I do, then that's kind of like trying to learn how to play piano by watching somebody else play the piano. So you got to do some of it on your own. And this is a good example of that. So anyways, I'm going to get started with this one. So if we want to graph y equals 10 to the x and also y equals log of x by filling in these tables. So 10 to the power negative 2 is what's going to go in here, which that's the same thing as 0.01, 1 divided by 100. That's going to be a point on the graph over here. So if this is 1, 0.01 is so close to the x-axis, it's basically on the x-axis right there. This is going to be 10 to the power negative 1 is 0.1. That's going to give you a point which is about like that, still quite close to the x-axis. 10 to the power 0 is 1, 10 to the power 1 is 10, 10 to the power 2 is 100. So we've got that point, and then 10 to the power 2 is way off the charts. So this graph is going to look kind of like this. And here it's going up super steeply. So that is y equals 10 to the power x. All right, so now for this one, let's see. To fill in what goes here, this result is going to be log of 0.01, replacing x with that 0.01. And whatever this is, remember, log of anything is the exponent of 10 that results in 0.01. And what is the exponent of 10 that results in 0.01? It's negative 2. We have it over here. So that's negative 2. So that gives you the point where x is 0.01 now. The y is negative 2. So that's a point that's very close to the y-axis there. And what is the exponent of 10 that gives you 0.1? That's going to be log of 0.1. The exponent of 10 that results in 0.1 is negative 1. Likewise, here, the exponent of 10 that results in 1 is 0. So that's going to be 0. The exponent of 10 that results in 10 is 1. The exponent of 10 that results in 100 is 2. And hopefully you see the symmetry between these tables. Basically, the x and the y coordinates are basically switched. So we have, so whatever was an xy point over here is now a yx point. And so if x is 0.1, y is negative 1, it's going to be about here. If x is 1, y is 0, that's right here. If x is 10, y is 1, that's over here. And then if x is 100, it doesn't fit here, it would be way off on the right over that way. We would get to y equals 2. So a rough sketch of this graph. So everything that was an xy point over here, the x's and the y's basically swapped. So it had a horizontal asymptote. It was getting really close to the x-axis when x is negative. Here, it's getting really close to the y-axis when y is negative. So that's the way a graph of a logarithm looks. Okay, now for exercise 4 and 5, these two kind of go together. What we have are some expressions that all involve log of 10 to the power 3 and log of 10 to the power 4 in one way or another. And I want to see which of these are the same is the goal of this. That's what exercise 5 is, to see like which ones of these rules generally work. Like if you have logs of different numbers, how can you combine them? So after I do a few of these, I'm going to go to exercise 5 and see which ones it looks like come out the same. Okay, so log of 10 to the power 3 means the exponent of 10 that results in 10 to the power 3. This whole thing is just 3. Likewise, log of 10 to the power 4 is just 4. So this is just 3 plus 4, and it's 7. You could think of this as using the inverse properties rules here. The log and 10 to a power basically cancel each other out. So this one comes out to be 7. Now this one, we can't just cancel out the log and these powers because we don't have it as 10 to a power yet. But we could cancel it out if we could combine them into 10 to some power. Now how does the 10 to the power 3 and the 10 to the power 4 combine? Using just exponent rules. Remember, if you have a to the power m times a to the power n, in general, you just get a to the power m plus n. Remember, 10 to the power 3 really means 10 times 10 times 10, 3 times. 10 to the power 4 means 10 times 10 times 10 times 10, 4 more times. So the total number of 10s that you have is 7. So this is 10 to the power 7. And once you write it that way, you can then use the inverse properties and say this is just going to be 7. Okay, so it looks like both A and B are sort of doing the same thing. You're adding up the 3 and the 4s in a different way. With B, you're adding up the 3s using the exponent rules. Here, you're just doing the logarithms first and then adding up the 3 and the 4. So let's look at, is there one of these rules that says that those would be the same thing? It looks like, oh yeah, if you multiply inside the exponent, that log of AB looks like what we're doing here. And the log of A plus B is what we did for the first one here. So we're going to draw a box around this rule. Now what about these other ones? Is log of that are sort of related to this? Does this one a rule? Is this third one a rule? Let's see by calculating the other sides of those equations here. So with this one, log of 10 to the power 3 is 3, using the inverse property there. Log of 10 to the power 4 is likewise 4. And 3 times 4 is 12. Okay, so this is not equal to 7. So that looks like this is not a log law. Okay. Oh yeah, so these important properties, I like to call them log laws because it sounds funny. You can call them log properties if you want, or log rules, same thing. So we could say this exercise is the log law or log gnaw exercise. So this one is a log gnaw, bro. Alright, let's go back to this one. Log of 10 to the power 3 plus 10 to the 4. So 10 to the power 3 is 1,000. 10 to the power 4 is 10,000. there's no exponent rule that tells you how to combine that into 10 to the 7 or 10 to the 12 or anything like that. So this is really just log of 1,000 plus 10,000, which is the same as log of 10,000 plus 1,000 is 11,000. And that, if you use a calculator, you'll get 4.04. It's not a nice even number or anything. And that is not the same as the result from B or the result from A or the result from C. So anything that has this has the parts of the logarithm being added together doesn't look like that turns into any other of these other nice things that you might want them to. So that means this one is log na. And anyways, let's go to E. Log of 10 to the power 5 using the inverse property, that's just 5. Minus log of 10 squared, that's just 2. So 5 minus 2 is 3. How about this one? Can you combine these exponents? What is it if you have like a to the m divided by a to the n in a situation like this? You cancel out n factors of a and you just get a to the m minus n. So you can apply that rule here to get, just simplify the inside first to become 10 to the power 5 minus 2, which is 10 to the power 3. And what's log of 10 to the power 3? That is 3. Alright, so E and F are both subtracting the 5 minus 2 in different ways. So which of these rules look like log of like 10 divided, or sorry, log of something divided by something else? That looks like this one here. We have something divided by something else. And what we got is that's the same thing as if you subtract those logs separately. Because we're either subtracting on the inside of the logarithm using an exponent rule, or subtracting on the outside using just subtraction of the results. And that looks like, yeah, that's what this one says here. So this one is a log law. Cool. All right, let's see. For G here, log of 10 to the power 5 minus 10 to the power 2. There's no nice way to combine the 5 and the 2 here. 10 to the power 5 means 100,000. 10 squared is 100. So this is just going to be log of 100,000 minus 100 is 99,900, which is going to be, you can get with the calculator. It's a little bit less than 5. 4.99956. Okay, so it doesn't give you 3. How about this one? If you do log of 10 to the power 5, the inverse property will just turn that into 5. The denominator just gets turned into 2, so you get 5 over 2, which is 2.5. Okay, so this doesn't turn into any of these other things. And part G didn't turn into any of these other things. So let's see which ones here are different. So log of A minus B, is that equal to log of A minus log of B? That would be like saying this one is the same as that, and those are not the same. So this is a log na. And what about log of A over B? Is that equal to log of A over log of B? Well, that's like what we did here to get that 3. And here's the doing the log separately and then dividing gives you 2.5. So it's not the same thing. So log gnaw. All right. Now let's go back up to I and j here. I want to try to do the same thing as before. Like, try to think of the thing inside the logarithm here as 10 to a power. How can we do that? Well, taking that 0.1 is the same as doing 1 over 10, or 10 to the power negative 1. 0.1 is the same thing as 10 to the power negative 1, and then that's to the power 5 in there, because, of course, 0.1 itself is the same thing as 10 to the negative 1. And to combine this into just 10 to a power inside the logarithm, this would be the same as log of 10 to the power negative 5, because remember the power to a power rule is what I call it. If you have something to a power and then that to another power, it means you multiply the powers. So I'm just multiplying the negative 1 times 5. So what is log of 10 to the negative 5? The inverse property says that's just going to be negative 5. Okay, how about this one? Well, yeah, log of 0.1 is negative 1, because 10 to the power negative 1 is 0.1. So log of 0.1 is the exponent of 10 that results in 0.1. So this is the same thing as 5 times negative 1. 5 times negative 1 is negative 5. So what you can see is both I and j here, in each of these cases, we're doing negative 1 times 5, but just in different ways. Here we're doing negative 1 times 5 using the exponent rule that says that's how you combine a power to a power. Here we're doing 5 times negative 1 because we're just doing log of 0.1 first. So then we get the same thing either way. So that is why this is a log law, this last one here. You're basically multiplying the t by the exponent of 10 that results in b in different ways. Now let's see some other things that might work out differently. If you just have log of 5 times 0.1, that would just be log of 0.5, and that, does that come out to anything nice? It's going to be like negative 0.301. And if you do log of 0.1 to the power 5, well, log of 0.1 is still negative 1 to the power 5. This just means negative 1 times negative 1 times negative 1 times negative 1 5 times, and that just results in negative 1. Okay, so K and L each result in things that are different from each other and different from I and J. So there are no nice log laws that involve things of this form. So that's what this last one here is. On the one hand, we have log of b to the power t, and then log of b first, and then doing that to the power t. This log of b and then to the power t is like what this one is. And that gives you a totally different thing than the way we got doing it here, where it came out to be negative 5. So this is a log gnaw. All right. These ones in the boxes here are kind of important rules that we're going to be using here and there in chapter 7. We got a lot of things in boxes in this section, so that's one sign that it is an important section to really understand. You might want to make flashcards for these. You can have a flashcard where on one side you have log of AB, and on the other side of the flashcard you have log of A plus log of B. That's a way to help memorize things like this. Alright, next in the next video, I'm going to do some examples of how to use these log laws. And I'll see you then.